Bismillah ar-Rahman ar-Rahim. So today we are with another lecture of the mechanics of material, and today we will be discussing beams. So beams are actually structural members which are normally used in civil infrastructure and also as members in machine as a machine parts. Here you see some examples of structural beams. The horizontal members here in this structure, the horizontal members are actually beams. The vertical ones are columns. So here also in this figure, you could see beams. This is a beam, and also this is a beam, and also these horizontal beams. So the horizontal members in the structure which supports the transverse or perpendicular loading, they are known as beams. The vertical ones are columns. These are the steel beams. Here in these two structure, you see steel beams. The beams are made of mild steel. However, here you see a reinforced concrete beam. So these are the beams which are reinforcing the civil infrastructure, and it is supporting the uh, roof and the top stories. So we call them reinforced concrete beams because inside the concrete we have steel bars which are used to reinforce the beam because concrete is a bad material in tension. So on the tension side, we have reinforced the concrete beam. Also here you see a structure, concrete structure, and you could easily see the beam. The horizontal ones are beams, whereas the vertical one is the columns. The vertical ones are columns. Some more examples of beams. Beams are also used in bridges. Here you see a railway bridge, and you could see the girders, which are used as a beam here. These are the steel girders, which are used as a simply supported beams here. Also, in this example, you could see the gigantic beams which are supporting the bridge structure, and also it will support the moving traffic. And the vertical ones are the columns. This is the column here, which is supporting the gigantic beam on the BRT overpass. So beams are structural members supporting loads at various points along the members. So loads are there at different points on along the length of the beam, and normally those loads are the perpendicular loads. Beams are normally in majority of the cases they are designed to take the perpendicular load. So transverse loading of beams are classified as concentrated loads or distributed loads. Applied load results in internal forces consisting of shear force from the shear stress distribution and the bending couple from the normal stress distribution inside the beam. So when the beams are subjected to loading, so because of shear forces, the beam is subjected to shear forces. We have shear stress inside the beam, and because of the bending that occurs because of the loading, bending stresses are produced, and those bending stresses produce the bending moment or bending couple. So this is the analytical model by which we could find out the bending stress inside the beam. Sigma x is a normal stress at a section, and it is equal to m. M is the bending moment, and I is the Second moment of the area, transaction area of the beam, and y is the distance of the point away from the neutral axis of the beam. The bending stress inside the beam is directly proportional. Sorry, the bending stress, that is the normal stress inside the beam, is directly proportional to the bending moment. So normally the criteria of beam designing is that we try to find out the bending moment, maximum bending moment, and the points where maximum bending moment, or the sections where maximum bending moment occur inside the beam. At that section, the bending stress would be maximum, and that is the more susceptible section where the beam would fail. Types of beams, so depending upon the supports, we could have a number of types of beams. Beams could be classified with respect to the types of support. And here you could see that one end of the beam is P, whereas the other is fixed. This type of beam is known as cantilever beam. Here, both of the ends are supported. Here we have an IFX support. Here we have a roller support. This is a simply supported beam. Overhang beam, you see that some portion of the beam is extended beyond the support, roller support. These are the roller support. This type of the beam is known as overhanging beam. Here we have more than two supports, knife edge support and three roller support. So this type is the continuous beam. Both ends of the beam are fixed. So fixed ended beam or fixed beam. This fixed three beam. And here one end is fixed, completely fixed, whereas the other end is supported by the roller support. So this type of beam is known as cantilever simply supported or fixed and simply supported beam. So we have simply supported beam, overhang beam, some portion is extended behind the support, and we have cantilever beam. These three beams are statistically determinate beams. We could solve the problems of these beams using the condition of equilibrium. And the continuous beam, fixed and simply supported beam, and fixed beam. These are statically indeterminate beams, meaning that in order to solve such problems because there is redundant reaction, we have to use the other tools to find out extra tools, because statically it would be not possible to completely solve such problems. So we would be using other criteria and tools to solve such problems, which we have already learned in our previous lecture. There could be different types of loading on the beams. So that is actually explained on this slide. Here you see that this is a beam, and beams are designed to take the transverse loading, perpendicular loading, and these are the supports. And here a load is applied, and this load is at a point, so at one point. So such type of loading is known as point load and point loading, or concentrated load, because the load is concentrated only at one point. So such type of loading is known as concentrated load or point load. So load types, effective force at load confined, meaning that the resultant load at the point of application or at the centroid of the load. Uniformly distributed load. Here the load is not acting at one point. It is actually acting over the whole length of the beam. And the intensity is given W. W is the load per unit length. Intensity we call intensity. So it is load per unit length of the beam. So we call it UDL, uniformly distributed load. And the resultant of this load could be the intensity multiplied, this intensity multiplied by length. So WL would give us the resultant of the load, and this resultant would be acting at the centroid of the UDL, and the centroid of the UDL would be in the middle, it would be here. So the resultant of this, the effective load, would be acting here. If this is L, so it would be at L by 2 from this side. So from this side of this support, the distance of the resultant load of this UDL would be L by 2. Triangular distributed load, as we see that the intensity of the load is increasing in this direction, and at this point the load is W. We call this triangular distributed load or uniformly varying load. It is known as uniformly varying load, as we see that load is uniformly varying as we move along the length of the piece. The resultant of triangular distributed load could be found by the equation of base into height. So here the base is length and the height, this height is W. So the resultant would be WL by 2, so half base is height, whereas the centroid of the resultant from this support, it would be at a distance of L by 3. So the centroid would be somewhere here, would be somewhere here, and its distance from this support would be L by 3. And from the other support, it would be 2L by 3. Causaridly distributed load. The load here is, let's say, WA, and the load at this support is WB, and between here you can see that the load is uniformly varying. The resultant of such load would be L WA plus WB by 2, and at which point this load would exert over the beam, the resultant load would exert on the beam. So from this support, it would be at the distance of L multiply WA plus 2 WB divided by 3 WA plus W. Point moment, it is also possible that we subject the beam to a external moment. So at this point, the moment M1 is exerted on the beam, which is at a distance A from this support. Normally, when solving the problems of beams or while designing the beams, we normally draw the shear force and bending moment diagrams for the beams. So the coming slides would be actually upon the topics which could be used that how to draw the bending moment and shear force moment diagram for the beam. So for that we use a sign convention. So let's say if we have a beam and it is exerted by forces, and we take a section. I'm cutting the beam into two portions. So we are visualizing that we are cutting the beam into two portions. So I'm taking this section. When taking this section, this is the left hand side of the section and this is the right hand side of the section. So if the left hand side of the section, if the application of the loads is such that if the left hand side of the beam or left hand side of the section appears that it should be moving in the upward direction, and the right hand side would be moving in the downward direction. So we term this as a positive shear. So the sign convention would be a positive shear. Whereas the reverse of this would be a negative shear. So if we take a section and the left hand side of the beam moves in the downward direction. It is moving in the downward direction, whereas the right hand side is moving in the upward direction. So we would term this as a negative shear. So here, if I take a section, this the left hand side uh, of the beam is moving in the upward direction, whereas the right hand side is moving in the downward direction, positive. If the left hand side is moving in the downward direction, whereas the right hand side is moving in the upward direction, negative. And if the moment is such that the beams bend like this, the concave is up, so we call it this is concave up. So if the concave is up, the bending is termed as positive bending. And if the concave is down, if the beam is bent in such a way that the concave side is down, so it would be termed as negative bending. So the sign convention is if the concave is up, positive bending, and if the concave side is down, we would term this as a negative bending. And if we take a section, the left hand side is moving in the upward direction, where the right hand side is moving in the downward direction. It would be positive shear. And on contrary, if the left hand side is moving downward, whereas the right hand side is moving upward, it would be termed as negative shear. So we will be using section method. So we would visualize cutting the beam into two or more sections. So here you see section AA. It is cutting the beam into two portions. And if we look at the portion of the beam on the left hand side of the section, the direction of force is upward. So it means that this on this side of the section, the beam appears to move upward, whereas on the other side it is moving downward. So the sign convention would be that this is the case of the positive shear. Action, the loading is such that the left hand side of the beam is moving downward, whereas the right hand side is moving upward, and convention negative shear. The beam is subjected to shear bending, and we have taken a section on the left hand side of the section. Here you see that the moment is clockwise. So we would take clockwise movements or clockwise movements positive on left hand side, and on counterclockwise movements as negative. Whereas on the other side of the section, this is the case of the positive bending because the concave side is up. If you look at the other side of the beam, right hand side of the section, here this moment is counterclockwise. So if you are working on the right hand side of the beam, and if the bending is positive bending, then on the right hand side, we have to take counterclockwise as positive, whereas clockwise as negative. So the summary is that on left hand side of the section, all forces, they are in the upward direction, you have to take them positive. Whereas all forces which are in the downward direction, you have to take them negative. However, on the other side of the section, the things would be reversed. All downward forces would be positive, whereas all upward forces would be negative. Similarly, here on the left hand side, all clockwise movements should be positive, all counterclockwise movements negative. However, on the right hand side, all counterclockwise movements you have to take positive, whereas clockwise you have to take negative. So in order to solve the problems or the beam problems or in order to draw the shear force and bending moment diagrams, first of all, what we have to do, we have to find out the reaction forces at the supports using the condition of equilibrium. So using the condition of equilibrium, first of all, find the reaction forces at the support. Then we have to use the section method. So depending upon the type of loading, we have to take a number of sections. And after taking a section, we have to consider either the left hand side of the section or the right hand side of the section. Selection of the section completely depends upon you. You could look at the problem and see which side you have to take so that your problem could be solved more easily. So if sometimes we look at the uh, beam and we could easily judge that if we take the left hand side, then it would be more easy to solve the problem in minimum time. And sometimes we look at our problem and we say that if we take the right hand side of the section, then the problem could be solved very easily. So you have to take a section. For shear force, perform algebraic summation of all of the forces on one side of the section. So shear force, for the calculation of the shear force, we have to algebraically sum up all of the forces they are acting on one side of the section. So if we add all of the forces on one side of the section, it would give us the shear force on the beam. Whereas if we sum up all of the moments on one side of the beam, it would give us the bending moment. The summation of all of the algebraic summation of all of the moments that are acting on one side of the section would be bending moment. So if the things which we have discussed, it will be more clear if we solve an example. So here in this example, you could see a beam. This is a beam A, B, B, C, D, and it is supported by two supports. Here we have a knife edge support. Here we have a support, and you could see two loading 20 kilonewton at the tip of the beam, whereas at point C, 40 kilonewton load is acting. The length of the beam is mentioned. The distance between point A and point B is 2.5 meters. BC is 3 meters. And CD is 2 meters. And the type of the beam, as this portion of the beam is extended beyond the support, so we are dealing with the overhang. Objective is what the shear force and bending moment diagrams for this beam. So first of all, what we have to do, we have to find out the reaction forces. So the external loading on the beams are in the downward direction. So we are expecting that the reaction loads RB and RB, that would be the upward direction. So this is RB, this is RB. And we have to use the condition of equilibrium to find out the reaction. And the condition of equilibrium are sigma Fy, summation of all forces must be equal to 0, and summation of all moments would be equal to 0. We are taking the summation of all moments at point B. So 40, this load times the perpendicular distance at this point, this load is producing a moment which is clockwise, and I'm taking it clockwise as I'm taking clockwise as positive. So 40 times, which is the magnitude of the force times the perpendicular distance. The perpendicular distance is 3. So 40 times 3 and plus for the clockwise moment. RD would produce counterclockwise movement. RD would produce counterclockwise movement at point. So RD times perpendicular distance or moment arm is 5. So minus RD And if we look at this force, it is producing a moment at this point which is counterclockwise, again minus 20 times moment arm, and the moment arm here is 2.5. It must be equal to 0. The only unknown in the equation is RD. So after calculation, RD comes out to be 14 kilonewton. Plus sign means that the direction which we have taken is correct. So RD is in the upper direction. Next, we have to use the second, the other condition of equilibrium, that is condition of all the forces must be equal to 0. And we are taking the upward forces positive. You could take the upward forces negative, completely depends upon you while finding out the reaction. So 14 minus 20 minus 40 and plus RB is equal to 0. And the only unknown is RB. From there, RB is equal to plus 46 kilonewton. Plus sign means that direction which I have taken is correct. Both of the reaction forces are in the direction. Once we have computed the reaction forces, then the next step would be is to take section and try to find out the shear force and bending moment about that section. So I'm taking section 1-1. Here you see that I have taken section 1, and this section would work from this point of the beam up to this support, that is point P. So this section would work from 0 meter. I'm starting, we are measuring the length from here. So this section would work from 0 meter to 2.5 meter. So this is the section, and let's say the distance from this point up to this section is x, and we could move this section from this point to up to point B, from point A to point B. So the x would work. This x would work from 0 to 2.5 for section 1, and we are taking the left hand side of the section. So this is the left hand side of the section, and the definition of the shear force is that the algebraic sum of all of the forces on one side of the section. Here we have only one force, which is 20 kilonewton. Secondly, the thing which we have learned is that on the left hand side of the section, all those forces which are acting upward must be taken positive, whereas all forces which are acting downward must be taken negative on the left hand side of the section. So this force is acting downward, so we have to take this negative. So generally, Vx for this section, which is at a distance x from point A, Px is equal to minus 20 kilonewton. So this x, as we discussed, that x actually works from point A up to point B, that is x works from 0 to 2.5, and V0 would be minus 20 kilonewton, and similarly V2.5. V0 is at this point, shear force at this point, and V2.5 is the shear force at point B. It is also minus 20 kilonewton. Actually, this equation is a zero order equation. Why it is zero order equation? Because here we have x raised to power 0. We have x raised to power 0. X raised to power 0, 1. So anything that has power 0, it is 1. We could put this x as 0. We could put this x as 2.5. So putting this x as 0, we get the shear force at point A, which is minus 20 kilonewton, and putting this x as 2.5, we have the shear force at point. Bending moment, general equation for the bending moment, the algebraic sum of all of the moments on one side of the section. We are taking the left hand side. We have only one force, so it is producing only one moment. At this section, if you see at this section, this force is producing uh, counterclockwise movement. So on left hand side, clockwise movement must be positive, counterclockwise movement must be negative. So minus mx is equal to minus for counterclockwise movement. And the moment itself is the magnitude of the force 20 kilonewton times moment arm. And here the moment arm is x. The distance of this force from this section is x. So minus 20x. If you look here, what is the uh, degree of the equation? 1. Here we have 1, but we are not writing. So 1. So the general equation for the bending moment for section 1 is nx is equal to minus 20x. And that x here, it is ranging from 0 to 2.5. So what is bending moment at point A, where x is 0? So putting this x is equal to 0. So m0 is equal to minus 20 times 0. So m0 is 0. And m 2.5, now putting x is equal to 2.5 minus 20 times 2.5. So the bending moment at a distance of 2.5, that is at point B, is minus 50 kilonewton meter. Now let's draw the shear force and bending moment diagram. For that, you have to first draw these horizontal, these vertical lines. So draw a vertical line passing through the concentrated load. So draw the vertical line passing through the concentrated load. And then for shear force diagram, I'm drawing a horizontal line. This horizontal line represents the center line of the beams. In other words, this horizontal line represents the beam. At point 0, what is at a length 0 at point A, what is the shear force? Minus 20. And this is also a datum line. So minus would be in the downward direction and plus would be the upward direction if we are drawing the shear force distribution over the length of the beam. So minus at this point minus 20. So let's say this is minus 20. So I get this point. And V 2.5, V 2.5 is this distance, 2.5 is again minus 20, so we get this point, minus 20 kilometers. And in between, throughout the section, the shear force is seen because we have 0-degree equation. So in between, there is no other loading, so shear force is the same. We will have this line. So our this from A to B, this is the shear force distribution over the beam. For bending moment diagram, again I'm drawing a horizontal line which is representing the beam. And at when L is equal to 0, bending moment is 0. When L is equal to 2.5, L is equal to 2.5, the bending moment is minus 50 kilonewton meter. So minus we have to take in the downward direction. So let's say if this is minus 50 kilonewton. And if you look here, the degree of the equation is 1. So here, if we plot this equation, it must be a linear line. So from this point to this point, draw a line linear line. Let's say I'm drawing a linear line. This is actually the bending moment distribution from point A to point B. The shear force equation here is 0 degree, and the bending moment equation is 1 degree. Remember that the bending moment equation would be always 1 degree more than the shear force equation. Here, this is a 0 degree line. The 0 degree line is a horizontal line, and 1 degree line is a linear line, linear equation. It is a linear equation, so if we plot it, we would have a linear line. So this is this distribution, the shear force distribution is a 0 degree. It is 0 degree, and this is 1 degree. So the shear force, the bending moment curve would be always 1 degree more than the shear force curve. So over this, if we move the section here, if we are moving the section from point A to point B, there is nothing, no discontinuity. The size of the beam is not changing, and also we are seeing no force. But when we reach point B and we move beyond point B, I see a reaction force here. So meaning that that section 1 would not work further. If we have seen a discontinuity of force, so I have to take another section to solve the problem. So we are taking now the second section. I'm taking the second section, and this section is at a distance x from point A, but this section would work from point B to point C. So section 2, and it would work from 2.5 meter up to 5.5 meters. So it would work from 2.5 meter to 5.5 meter. And now I will try to produce the shear force equation. And I'm taking the left hand side of the section. Definition of the shear force, the algebraic sum of all of the forces on one side of the section. So the algebraic sum of all of the forces on the left hand side of the section. Upward forces positive, downward forces negative. So Vx minus 20 kilonewton and plus RV we have already computed is 46, so in the upward direction, plus 46. So Vx, here it is a typo, so Vx is equal to minus 20 plus 46 kilonewton. So again, if we look here, the order of the equation is 0. Vx is plus 26 kilonewton. Vx is plus 26 kilonewton, and here x is to power 0. So in order to find out the 2.5 for this section, we have to put x is equal to 2.5. So v 2.5 is equal to minus 20 plus 46 kilonewton. So after calculation, it would be plus 26 kilonewton. So initially for the first section we were here. Now for the second section, we have shear force value plus 26 kilonewton. So plus 26 would be somewhere here. So we got this one. and V 5.5 would be again plus 26 kilonewton. V 5.5 is at point C, so again plus 26 kilonewton. And then since we know that we have a 0 degree equation, the order of the equation is 0. So, and the plot of 0 degree line would be a horizontal line. So we would join these 2 points by a line. And the degree of this line would be 0 degree. So this is the order of this equation or this line. So we now have a shear force diagram for. Next, we have to draw the bending moment diagram. So first, we have to develop the general equation. The bending moment is the summation, algebraic summation of all of the moments at one side of the section. We are working on the left-hand side of the section, and here we have two forces. This force would produce a moment at this section, and this force would produce a moment at this section. So mx is equal to this force is producing counterclockwise, and on the left hand side of the section, counterclockwise must be negative. So minus 20 times the moment arm, and the moment arm, so this is x, so 20 times x plus 46, and this is the moment arm. This is the moment arm. So this is x, and this is 2.5. So this distance is x minus 2.5. So the moment arm for RB is x minus 2.5. And it is producing clockwise moment. So plus 46 times x minus 2.5. So this is the general equation of the bending moment for this section. Next, we have to find out the bending moment at point B. So if we put x is equal to 2.5 minus 20 times 2.5 minus 20 times 2.5 plus 46, x is 2.5, so 2.5 plus 2.5. So x m 2.5 is minus 20 times 2.5 is equal to minus 50 kilonewton meter. The same moment, we got the same moment here. So if I plot this here, so this is the same point. M 5.5 is equal to, here now we have to put x 5.5. So minus 20 times 5.5 plus 46 into 5.5 minus 2.5. And after calculation, we would have plus 28 kilonewton meters. So F 5.5 is 0.3. F at a distance of 5.5 over the length of the beam, it is here, and we have plus. The plus would be above that line, and 28. So let's say this is plus 28. So we reach here. If you look at the general equation of the bending moment of for this section, again here it is 1, 1. So we have first order equation. So which means that if we plot this equation, we would have a linear line. So next we have to join these 2 points with a line, and this line would be 1 degree line. 1 degree. Next, if I move this section here, nothing is happening. But when I reach T, I see a 40 kilometer discontinuity of the force, which means that my section 2 would only work from 2.5 meter to 5.5 meter. So we have to take another section to further solve the problem. So I'm taking my section 3, and x would measure from 0 up to this section, and but my section itself would be working from 5.5 to 7.5. So it would work from C to D. At point C, the length of the beam is 5.5, and at D, the length of the beam is 7.5. And again, we have to write down the shear force equation and bending moment equation. So first, let's say write down the shear force equation, and we are taking the left hand side of the section. Summation of all of the forces on the left hand side is the shear force. So summation of all of the algebraic equation, Vx is equal to forces which are acting downward, negative, so minus 20. Forces which are acting upward must be positive, plus 46, and minus 40 kilonewton. So this is the general equation of shear force for section 3. Again, the order of the equation is 0. So order of the equation is 0. So we at point C, that is 5.5, x is to power 0. So V 5.5 after calculation is minus 14 kilonewton. V 7.5, in this equation we put x is equal to 7.5. Again we will get the same value, that is V 7.5 is equal to minus 14 kilonewton. So at this point we have to plot the shear force. The shear force is minus 14 kilonewton, so we have to move here minus below this horizontal line. So let's say this is minus 14 kilonewton. So this is V 5.5, and V 7.5 is also minus 14 kilonewton, and then we have to join these 2 points by a horizontal line, because the order of the shear force equation is 0. Bending moment equation, summation of all of the algebraic summation of all of the moments on one side of the section. We have taken left hand side, clockwise moment positive, counterclockwise moment negative. This force is producing counterclockwise moment from minus 20 times perpendicular distance. At this section is x, so minus 20x plus this force is producing clockwise, so positive, so plus the magnitude is 46, and this distance is, this is x, from x I have to minus this, so we will get the moment arm for this force about the section, so x minus 2.5, and we have this force, and it is producing counterclockwise moment about the section, so it is minus 40 times moment arm. This is the moment arm. So from x we have to minus this distance, and this distance is 5.5. So this moment arm is x minus 5.5. X minus 5.5. So this is the general equation of the bending moment for section 3. Now, if you look at the equation again, the order is 1. So it would be a linear line. The plot would be a linear line. M 5.5, if we put 5.5 for x, and after calculation we would get plus 29 kilonewton. So at this point for section 3, the bending moment is plus 29 kilonewton. And 7.5, so for instead of x we have to plus 7.5, 7.5, 7.5, 7.5, and after calculation we would get 0. So the bending moment at this point D is 0. And if you look at the equation, it is first order equation, so the plot would be linear. So draw a line. So now here you could see that we have drawn the shear force diagram, which is known as the bending moment diagram. This is the shear force distribution over the length of the beam, and this is the bending moment distribution over the length of the beam. Here, the shear force is negative. The shear force is negative on, and here you could see that in that portion of the beam, the shear force is positive. Again, the shear force is negative. If you look here, this bending moment distribution is below uh, the datum line. So this is a negative bending moment, and this is a positive bending moment. Negative bending moment would be the concave would be down. Positive bending moment, the concave would be up. So we have shear force diagram, bending moment diagram. We could also draw the deflection curve, that how the beam would beam bend. So if you look here, uh, these are the erection supports. At the erection support, the deflection would be zero. So here the deflection would be zero. Here the deflection would be zero. However, the deflection would occur in between these 2 points and also here. So if we expect that how the beam would deflect, so we are expecting that because of this loading, this beam would deflect, and it would be like this. Here the deflection would be zero, and then we would have a deflection like this, and then again the deflection at point D would be zero. So this would be somehow the deflection curve. So this is the deflection curve of this beam. We are expecting that this beam would deflect in this manner because of this external loading and these two supports. So if now we compare this deflection with our bending moment diagram, so here the bending moment is negative. The bending moment is negative. So we are expecting that the bending deflection would be the concave would be down. If you look here, this is the beam bending. The concave portion is down. Concave portion is down. So that's why bending moment is negative. And from here, if we look from here, from this point, the concave portion is up. Concave portion is up. So we have positive bending moment. So we could, from bending moment diagram, we could easily also draw the deflection curve. So how would be the deflection curve? So with this, I'm finishing the lecture. Thank you.